Okay, welcome back, everyone. Today we take kind of a step back or detour back from general relativity, which will be relevant again in about next week and the week after that when we do explosions and cosmology. But for now, we have to kind of set the stage for those farther things in the universe by talking about things farther away in the universe. And the first of those, the first thing that's beyond our local solar system and other stars around us, is really getting a concept of the galaxy. First our own, and then other galaxies. So that's today's topic. Today we talk about what are galaxies, how we know what they are, where they are, and what can we learn about them. So pictured here is the Messier Catalog. We already showed this picture, I think, in the second week of the semester, talking about what's beyond the solar system. And as you might recall, Messier made this catalog of 110 objects, which are definitely not comets. And we can obviously now see these are not comets. They're not some objects traveling through our solar system. They're not individual stars. They are something else. Not all of these are the same. We can see different types of objects pictured here. You'd notice, for example, the top line is what we will come to call stellar clusters, or most of them globular clusters. So that is spherical clusters of many, many stars. Today, we know many of the images, like the ones appearing here at number 31, M31. This today is what we call the Andromeda galaxy. Back then, it wasn't called that yet. They didn't know what a galaxy was at the time. But 33 is another spiral galaxy, as well as 51, 66, 100, 101. We see a lot of these, 81. Many of these objects we today recognize even from our popular science background. We see these as galaxies. So these are spirals. Not all galaxies are spirals. And in between, we see other types of objects. For example, 16, 17, 20, and M8. These objects have this kind of misty appearance, and they're called nebula for their misty or nebulous cloud-like appearance. So this catalog, for already hundreds of years old, required a telescope to produce, but it shows many objects that are definitely not just individual stars. We have here clusters, nebula, galaxies, more interesting objects or different objects than just the stars we had been discussing up to this point of the course. So today we'll talk about these types of objects and how we understand them, how we analyze them, and how we come to understand what they are today. Starting with our own galaxy, maybe one of the most prominent features in the night sky for a very long time in history. Difficult to see today. If you live in a populated area, in a city, then the lights around the city will typically dim out or outshine the galaxy, this galactic plane. But up until 100 years ago, it was almost impossible to miss. It's a long path or lane of light, white, bright color, crossing the night sky from side to side. The Greeks, of course, noticed it as well. They gave it the name, the Galacticus Kyklos, the cycle of milk. Basically, the word galaxy comes from the Greek word for milk. You might know it today from lactose intolerance or galactose, the sugar in milk. Am I recording? Did I forget to record? No, I'm recording. So the same word in Greek gave its name to what was then the galaxy, the only one, the Milky Way, the path in the sky that looks like kind of someone spreading milk across the sky. In ancient mythology, it was actually considered to be milk sprouting out of the breast of one of the goddesses, and they didn't quite know exactly what it was. There were many different opinions as to what it was, and some of them did already back then propose that it was indeed composed of many, many faraway stars. That is, that the reason it looks like this thin veil in the sky is because there are so many stars that are so far away that their light gets kind of blurred into each other and we can't tell the individual ones apart. But this notion that it is composed of many, many individual stars, which today we know to be true, was already raised by Anaxagoras and Democritus in as early as the 6th century or the 5th century before the Common Era. On the contrary, philosophers and scientists like Aristotle claimed that it was actually nearby stars that are just very large. So not many, many far away, but fewer ones that are close by and are large. This was accepted for a while, but kind of many different opinions lingered on for a very long time. This recession, going away from the Aristotelian view back to the understanding that these are, or the proposition, that these are many, many distinct stars, developed throughout the what's called the Arab or Muslim Golden Age. We mentioned many of these scientists and philosophers when we talked about the Copernican revolution and building up to the Copernican revolution, realizing that there are indeed these many stars in the Milky Way. But the first one to actually point a telescope at them and see those stars individually apart from each other to actually make out the stars making the Milky Way was Galileo Galilei. As we recall, the first astronomer to use a telescope for astronomy. And among his many, many other discoveries, he discovered that the Milky Way was indeed composed of many, many stars. This led later to the kind of romanticization of the concept. Immanuel Kant famously said that the Milky Way was an island universe. The entire universe is kind of an island on its own, composed of many, many, many stars. Today, we estimate their number at over 100 billion stars. Okay, realizing what the galaxy was made of still didn't tell us what it was shaped like. What was the actual construction of the galaxy? Because in the sky, again, it just looks like this lane of white, now we know of many, many dots of stars. But this picture, which of course today we see in all sorts of popular media and we associate with the galaxy, is of course not an image of our own galaxy, of our own Milky Way. It can't be, because we are part of the galaxy. We can't see the galaxy from outside, as George Lucas painted here. And Herschel, William Herschel, was really the first one to try to mathematically study the structure of our own galaxy, of our Milky Way. And the way he did this was by counting stars in the sky, the density of stars that he could see with his telescope, on the Milky Way and moving away from the Milky Way. That's what this table here on the left, which is Herschel's original table from his book on astronomy, Outlines of Astronomy, did. So the table here is sorted by galactic latitude. That is, if you see the plane in the sky, you can take the angle either on the plane, that will be angle 0, or off the plane, up to 90 degrees, which is perpendicular to where we see the galaxy in the sky. And what he saw, that if he counts the average number of stars at different angles from the galactic disk, here given in a field of 1/4 of a degree, 15 minutes of arc minutes in diameter, then the density of stars grows when you approach the disk and diminishes when you turn away from the disk. So there are many, many more stars, about, what's this? About 30 times more stars in density per angular unit, angular square in the sky, in the direction of the Milky Way versus perpendicular to the Milky Way. On the left here, you can see a similar table to this, a more modern one from the 20th century, so about 150 years after Herschel's discovery, which adds another degree of complication. It sorts the stars not only by galactic latitude, but by magnitude. So of course, there are fewer low magnitude stars than high magnitude stars. The lower magnitude stars are brighter. The farther you can see into space, that is, the better your telescope, the lower the magnitude, or the higher magnitude, the less the brightness that you see, but the higher magnitude, the more stars you can count. And this is of course a monotonous feature. If you increase the magnitude which you can see, then you'll see more stars at whichever angle you look in the sky. If you can see, you have a better telescope, you can see less bright objects, so higher magnitude objects, you can see more of them because you can see further away. But the other trend is that while at every angle you can see more stars, many more stars, the deeper you look, you also see that the higher you look away from the galactic plane, the fewer stars you count, while towards the galactic plane, you can count more and more stars. Okay? So again, we have this geometric construction where there is no spherical symmetry. If there were spherical symmetry, you'd expect the number of stars, or the density of stars per area in the sky, to be the same at every angle to which you look. But we don't see that. We see a definite preference for the plane of the galaxy. That is, the same lane we see in the sky is the densest region in the sky in terms of stars per angular area. Fewer stars as you turn away from it. So Herschel already had a basic count of this. And from this, he concluded two things. The first of them was that the galaxy was in fact flat. It was a flat construction, basically a disk. It's not completely flat. It's not one star in width, but it's much more flat than it is wide, which means we are sitting in the galaxy. And if we look into the plane, then as you look into the depth of the plane, you have a lot farther to go. You'll see many more stars. Then if you look perpendicular to the plane, going out, and then very quickly, you'll kind of look outside of the galaxy. And so won't see anything anymore. You'll see a lower density of stars. So this is how Herschel concluded that the Milky Way was a galaxy. We were on it, and it's flat in shape. That was correct. The planar structure of the galaxy. His second conclusion was incorrect. He concluded that we are at the center of the galaxy. And the reason he concluded that can be shown in his original diagram here at the bottom right, mapping the stars around us. And what we can see from his diagram, the galactic plane here is represented by the horizontal axis, and the perpendicular going out of the galactic plane is the vertical axis. And so indeed we see that he correctly captured the flatness of the galaxy. This object is longer to the sides than it is kind of bulky at the top and bottom. But he did measure, as far as he could, the same density of stars in our vicinity. So to the left and to the right, and if you want to the inwards and outwards, on the plane, he measured the same density in all directions. And of course, the only object which is the only way that an object will be symmetric in all directions on a plane is if it's in some sense circular or roundish, and you're close to either the exact or close to the center of the circle. Okay, so these are two symmetry arguments, complementary ones. There is no symmetry in the angle out of the plane, and that's what indicates that the shape is in fact a plane. But there is symmetry in the plane, around the axis perpendicular. And from this, he concluded that we are the center of the galaxy. Any questions so far?
Are we?
Of course not. There's a big red X here. Of course, we're not at the center of our galaxy. There's a huge black hole in the center of the galaxy, 4 million times the mass of the sun. So we're quite lucky not to be at the center or around the center. And we'll talk about the next stage of understanding that mistake, of understanding how we know we are not at the center of the galaxy.
Jose,
yes.
Can you explain again how we I mean, by the measurements, I understand how we made the measurements, but how do we derive the results of them?
How do we derive the results, or how we make the measurements?
No, how we derive the results from the measurements.
Okay. Let's see if I can switch to the tablet. Okay, do you see the screen?
Yes.
Okay, so we are here. And we look at different directions. And what do we see? We see a lot of stars here. Very few stars here. Now let's just take two models. Let's take the model of a spherical shape and the model of a planar shape. If we had a sphere, and there's no reason to assume that the density varies around the sphere. So if it were spherical around us, then we would see an isotropic distribution of stars. We'd see the same density in every direction. We don't see that. What we see fits something more like a plane. So this will be the axis. The plane is not entirely flat. It has some bulkiness. It has some width. Let's make it like this. And now if we are on this plane, looking in the plane, we can see quite far. We'll in fact say that this could be several tens of kiloparsecs. So we can see the stars quite far away. That means there are a lot of stars to be seen. If, on the other hand, we look up, then very quickly, we're looking past the edge of the galaxy, basically, and into space. So there are a lot fewer stars along this direction than along this direction. Okay, so the shape, and of course it varies. In between, there's some middle number over here. So the galaxy is some disk with a finite small width, but a much larger radius. If we look along the radial direction, we see a lot more than if we look perpendicular to the radial direction. And then the galaxy ends. The galaxy just runs out, and we're basically seeing past the galaxy into nothing. Okay?
Okay.
And the next item, as we said, was that since in the disk itself, looking around the disk, it looks symmetric to us, then we can conclude, or Herschel concluded, that we have to be at the center of the galaxy, because if the galaxy were, for example, if the galaxy looked like this, then again, we find that looking towards the center, we will be looking at a large, wider length of stars. We will see many more stars looking to the left here than to the right. To the right, we will very shortly exit the galaxy and look again into the nothingness of space. And because we don't see that, because we see, or he saw a symmetric distribution of stars around us on the galactic plane, he concluded that we were at the center of the galactic plane, or the center of the galaxy.
But if maybe the galaxy is also has the same density all around, even when it's a disk shape.
So that's a possibility. Of course, when you start complicating the model, you can add more alternatives. And one of them is indeed that the density is not the same. But then consider philosophically or mathematically that if you look in every direction and see the same density per area of stars, then if you're not at the center of the galaxy, that is, if you see the same density in every direction, one possibility is that you're at the exact center and the galaxy is homogeneous. So the galaxy has the same density everywhere, you're at the center, so the integral is the same in every direction because you're basically integrating the same number in every direction. The alternative is that you are not at the center of the galaxy and that the density changes exactly in the correct amount to compensate for your being off center. That is, the density here would have to be highest. The density all this way would have to be much lower so that you count the right and left and giving the same total number of stars. And you'd need an intermediate density here. Oh, sorry, it will be intermediate density here, a lower one here, an even lower one here. And basically you'd need to make out the whole density in the galaxy in every direction to exactly compensate for your position in it. And that's a very strange way to build the galaxy, right? It means that the galaxy is not uniform, but it's non-uniform in the precise, correct spherical distribution in 3 dimensions to make us think that we're at the center because we see the same thing in every direction. So you kind of have these 2 alternating models. Both of them should make us feel uncomfortable. The first, why should we be at the center of the galaxy, right? Copernicus already told us that we are not special. The Earth is not at the center of the solar system. Why would now the sun be at the center of the galaxy or the center of the universe? Kind of makes us feel uncomfortable. But that's still not as bad as us being off center in the galaxy, but the entire galaxy distributing its mass and stars to fool us into thinking that we are in the center. Okay, so in the ladder of improbabilities, that was considered to be much less likely. So the data suggests that the simplest explanation, even if it feels weird, the simplest one is to assume a basically homogeneous galaxy and that we are at the center. Okay?
Okay.
Okay, so let's see where that does break. Let's switch back. And to understand where that breaks, we'll present another early 19th century result or paradox or something that made scientists feel uncomfortable with the results. And that's called the Olber's paradox about the infinite universe. And in the most basic terminology, it goes like this. Assume that there's some fixed density that's basically constant for stars in the galaxy or in the universe, it doesn't matter. Some fixed density rho. Again, it doesn't mean that it's exactly the same. Obviously, if you look halfway between the sun and Alpha Centauri, there's nothing there. it's the nearest star, there's nothing in the middle, so you'd have a density of almost 0. If you look in the sun, you'll have a density of 1. But on a large enough scale, if you average out over a few parsecs or a few tens of parsecs, you expect the density not to change too much. That's kind of a reasonable, nothing should be too crazy assumption. So you assume a fixed density of stars per volume rho. You then assume a typical luminosity, average luminosity per star, say some capital L. And again, this can have some factors. You can average out on the distribution, but assume some average L that at least shouldn't depend on direction. It should basically be the same if you average over enough stars in any direction in the sky. Because the flux, as we saw, decreases with r squared, with the distance from the source, like L over r squared, that's just conservation of energy flux exiting any sphere. The surface area of the sphere is 4 pi r squared. So if you have energy L from the center, you'll have L over r squared coming out of it as flux at any radius r. If you look at the number of stars at radius r, or on the same spherical shell of radius r, then it'll go like rho r squared. Because if you assume a constant, a fixed density, then that is a volume density. And if you take some spherical shell at radius r of some width dr, then the volume of that shell will be 4 pi r squared dr times rho, will give you the number. And so it goes like rho r squared. These calculations are very similar to the ones you've been doing, I guess, since first year in electrostatics, Coulomb's law and Gauss law and flux. Obviously, if you have a constant density, then the number, or the density of stars, the number of stars will grow like r squared. The flux from each of them will decrease like r squared, which means if you want to calculate the full flux you can measure at the Earth from the entire universe, you will do that by integrating outwards in r, integrate over r from Earth 0 to infinity. The number density of stars you accumulate at radius r times the average flux of each of those stars, which is L over r squared. So you take all the constants out, and what you find out is that you're integrating over r squared in the numerator from the density number of stars. You're dividing by r squared by the reduction in flux by distance, which means you're integrating over just the function 1, basically integrating over dr from 0 to infinity, and that gives you infinity. Okay, this is sometimes called the dark sky paradox, or the infinite universe paradox. They come together. Because what this kind of rough calculation tells you is that if the universe is infinite, and the density of stars is basically some average across the universe, and you're seeing all of them, you're just seeing less and less of each, with the flux decreasing by r squared, or 1 over r squared, then the integral in every direction in the sky should be infinite, and the sky should be basically white at night. Okay, because there's an infinite flux coming from every direction. Is the calculation clear, and is the paradox clear? That is, we do not see a white sky at night, right? We see a dark sky. Okay, so this was in this mathematical form. It was formulated by Olbers and was named the Olbers paradox. He wasn't the first to actually think about it. Kepler already made the similar calculation and estimate with his telescopes in 1610. He solved the paradox very simply by saying the universe is not infinite. The universe has to be finite, because otherwise we would see infinite light from any direction in the sky. Newton kind of tried to play with this as well. In his Principia Mathematica, he makes a very similar table to the one that Herschel made, counting stars by magnitude and seeing that the number increases like rho squared, like the volume of not the volume, like the surface area gained at radius r. Only you can see if you look at the draft of the Principia that he does this for magnitude 1, magnitude 2, magnitude 3 as the radius, the length to which you can see grows. And then at some point it stops working. So he cuts off those lines and edits out the table. So even Newton was kind of fiddling with experimental results at that point. But he saw the problem. He saw that this growth law would be problematic and has to stop somewhere. Olbers, like I said, formulated this paradox in 1823. And his solution or proposed solution was that the universe was indeed infinite, but we don't see the faraway stars. Something has to be on the way of the light between the stars and us, and has to block out the light, absorb, dim, scatter. Something has to block out the light, so we can't actually see infinitely deep into the universe. Poe in 1848 also gave an explanation, a proposed explanation. He said that the universe was infinite, but because light has a finite velocity, and at the time in the 19th century, you surely remember, the universe was considered to be quite young, right? Who remembers how young people thought the universe was in the mid-19th century? So Newton thought it was 6,000 years old, following biblical sources and other religious texts and calculations. And as you recall, it was only geologists, Darwinists, evolutionary biologists, who started pushing the numbers up towards the tens and hundreds of millions of years for the age of the Earth. And the physicists actually were reluctant to accept that. Recall the discussion, I think we had it on week 5 or something, of Lord Kelvin objecting and claiming the universe was actually much younger, or giving an intermediate number. 30 million years was the Kelvin estimate for the Kelvin time duration of the solar system. So at the time, it was accepted that the universe was quite young, and they already knew the speed of light. By that point, established as about 300,000 kilometers per second. So Poe said, sure, the universe is infinite, but the light has not reached us yet. Today, this kind of explanation wouldn't fly because the universe is today billions of years old, and we do think the light has had a lot of time to reach us. And today we see things that are billions of light years away. The 20th century and relativity gave with it a new explanation, the cosmological explanation, which was that the expanding universe, or rather the stretching universe, we'll talk about that in 2 weeks in our final class about cosmology, caused light from faraway sources to shift to the red, that is, lose energy. And so this is kind of a dimming mechanism, which says all the light is reaching us from very far away, but it becomes weaker and weaker as it comes close, which is kind of fixing this integral, reducing it to a finite value, because very, very far sources are being dimmed out by gravitational redshift. Okay, so those are kind of the possible explanations. I'll just comment that today the universe is accepted as infinite, so Kepler's explanation is no longer regarded as relevant. We talked about Poe's explanation. Today the universe, we think, has been old enough for a lot of light to reach us. And redshift from the expanding universe isn't quite relevant on the local scale. On the galactic scale, it's not relevant. Even in our local neighborhood of galaxies, it's not strong enough to overcome gravitational attraction. Galaxies in our vicinity are actually coming close to us. So the correct explanation, at least for why the galaxy looks the way it does, and this was also related to Herschel's mistake, is really the Olbers explanation. Something on the way of between the stars and us is dimming out the light and making the sky dark for us. So what is on the way between us and, and other stars in the galaxies. Well, the first thing is what was already known at the time, and that's nebula, nebulae. Nebula singular, nebulae plural. These kind of dark nebulae are nebulae. Here on the bottom left, a very famous nebula. This is called the Barnard 68 interstellar cloud. This is Edward Emerson Barnard pictured here on the right. We mentioned him as well on the second week this semester for discovering Barnard star, the closest star to us, closer than Alpha Centauri, I think. I don't remember exactly, but close enough, very, very close, but we cannot see it without a telescope. It's very, very dim. So he made a lot of discoveries with the telescope in our vicinity, and he found this nebula, the kind of dark cloud in the sky. Today we would call it either a dark nebula or an absorption nebula. It absorbs the light coming from behind it. Right? It's clear to see in this left image that the approximation of basically homogeneous sky or universe is quite a good one. We don't see a big difference in light coming out in these different directions, but the nebula blocks out some of the light quite clearly, right? We see that there's a cloud, and just like we cannot see the sun on a cloudy day beyond the clouds, here we don't see the stars beyond this nebula, blocking out the light from behind it. It's the opacity in the gas in the nebula which is blocking the light from behind. Okay. On the right here, we see another famous nebula, part of the Orion Nebula in the constellation of Orion. This feature is called the Horsehead Nebula because it resembles the head of a horse. And many, many famous pictures today in astronomy are indeed pictures of these nebulae because they're very pretty to see against the sky. And as we will see, they also have a very dramatic effect on coloring. This gas will oftentimes be associated with dense gas with regions that can emit strong light, star formation regions. And so we'll see these kind of bright sources in blue close to dark patches or redder patches around these nebula. So although the universe seems homogeneous, at least our vicinity seems homogeneous in distribution of stars, we cannot integrate all the way out to a star because in the middle, there's an obstruction. A dark nebula like this can block out or dim the starlight. As I said, close to very hot stars, the gas, the hydrogen in the nebula can be ionized. So H2 is the second ionization, or basically fully ionized hydrogen. Non-ionized hydrogen or neutral hydrogen is the first ionization level, so it's called H1. And so we already have these different types of nebula, and the constitution, whether it's ionized or neutral hydrogen, will affect the opacity and scattering processes, which will affect the color and the radiation coming out through these nebulae. Again, responsible for all these spectral and coloring effects. Okay, so that's the first thing that's on the way. Nebulae typically will scatter more blue than red light. And that's similar to the Rayleigh scattering that we talked about and that we know from our own atmosphere, which is why, for example, we might often see these blue and red features mixed with each other. For example, here in the Crab Nebula M1 in the Messier Catalog, this is the nebula surrounding the remnant of the supernova explosion at 1054, the Chinese nebula. There's a pulsar in the middle, which you cannot see with the naked eye. We'll talk about him next week. But we can see that there's kind of blue light and red light intermixed with each other. The hot parts of the nebula heated by either white dwarfs or neutron stars, supernova remnants, they heat the nebula around them, producing stronger color, bluer color, red comes from farther away. Another example we can see here, the Cat's Eye Nebula with its different coloring. And in general, like we see on the left or right, star-forming regions, new stars shine in light. We can see the blue and red coming from different parts of that region in the sky, basically tracing the shape of the clouds, of the gas clouds in these nebula. Okay, any questions? Okay, again, the red light here, in this case, comes directly to our eyes, so it can come through the nebula. The blue is often more dispersed, like the blue in the sky, highly scattering. Okay, the interstellar medium, or the ISM, is another source of opacity or dimming for light coming from other stars, from far away. Typical densities of the interstellar medium can be quite low, from fewer than 1 atom per cubic centimeter up to maybe 100 atoms per cubic centimeter. The average interstellar medium density is about 1 atom per cubic centimeter. If you want a comparison, a typical gas on Earth, you would measure densities in Avogadro's number, right? The 10 to the 23 atoms per what's called a mole of matter. So you'd have about 20 or more than that orders of magnitude of density higher even in the air that you breathe compared to the interstellar medium density. It's very, very sparse. It's almost entirely gas, and that is, of course, mostly hydrogen and helium, trace amounts of other gases. Typical temperatures are about 100 Kelvin. That's most of the interstellar medium. But there are regions of it, or some part about 100th of the interstellar medium, which are larger particles, dust particles. These dust particles can nucleate around higher mass atoms, like carbon or even silicon. Of course, carbon, the remnant, the end result, or one of the results of nuclear burning in stars after the main sequence. Eventually you reach carbon. After helium, hydrogen to helium, then helium to carbon. Silicon is much rarer. Silicon is the result of the last stages of nuclear burning in stars, just as the star is going to die and go away as a supernova. These supernovae explode and spread these heavy elements across the universe. And around these original atoms for nucleation, the dust particles can accumulate more and more elements and sometimes even molecules. And some of the research going today, as we mentioned, into astrobiology and the possibilities of chemistry in outer space, concentrates on these dust particles in the interstellar medium as kind of these beds for stitching on other types of atoms and undergoing nuclear reactions. So even though they're only 1% of the particle or of the mass of the interstellar medium, and they're quite cold, only about 10 degrees Kelvin, they can still have some interesting chemistry. And what they can do is, of course, scatter light, dim, absorb, and scatter light at various frequencies. And that's what we see if we look, for example, at a galaxy. Again, any galaxy that you see head on is not our own. This is M74, the Phantom Galaxy. And you can see these dust lanes. What's known today as these spiral arms of stars and darker, redder dust lanes in between. Okay, so we see both spiral arms and dust lanes together composing the Milky Way. Okay, so in the Milky Way, this interstellar medium, although it's very, very sparse, is what occupies most of the volume of the galaxy in between the stars. And so even though it's very sparse, there's much more of it. And so about 15% or 1/6 of the galaxy, or rather of the stars in the galaxy, of the mass of the stars is actually interstellar medium and not stars. So much of the what's called the baryonic matter, the matter that we know, who we know from particle physics and chemistry, about 1/6 of that in the galaxy is interstellar medium. And as we mentioned, it can absorb light. In astronomy, we call this extinction because the light doesn't reach all the way to our eye. It goes extinct on the way due to these absorption and scattering mechanisms. The temperature of these clouds in itself is a source for infrared radiation, that's black body radiation, as well as different types of microwave and spectral lines common to this mostly hydrogen clouds. We mentioned the 21 centimeter line, I think in one of the tutorials. And of course, scattering. Okay, we also mentioned the Rayleigh scattering effect, which is that these particles tend to scatter blue light more than they scatter red light. And that means that if we look at something like the same Bernard's 68 cloud from before, but now we look at it not only in visible light, but in infrared light, in infrared radiation, then now we see that indeed this nebula is scattering the blue light and the visible light, but the red is still there. There are still sources of stars and starlight even beyond the nebula. And in fact, the universe does appear to be homogeneous in this region. It's just that the nebula on the way is blocking the blue and visible light. It's letting the red come through. Okay, so this is kind of the ultimate proof that it is in fact a dimming process or a scattering process, which is preventing some of the light from coming to us. Okay, this extinction mechanism. Okay, and we already mentioned that the sky is blue, the sun is red at sunset, and yellowish, more yellow than its black body color would determine. All of these are effects of these Rayleigh scattering effects through clouds of dust in nebula and in the interstellar medium. Any questions? Okay, in that case, let's take a short break and continue at 1 o'clock with more of the things we can find in a galaxy. Okay, so we started today's talk with showing the Messier Catalog, 110 objects. We talked about galaxies, or at least by now we're kind of getting the idea of our own galaxy, which is of course not in the catalog because we are on it and we don't see it as a galaxy. We talked about nebula, which do appear in the catalog, and we saw many pictures of a few of them. Very pretty pictures, again, because the shape of the cloud can be very amorphous, and the different scattering processes of light in different wavelengths, the blue and the red, often create very dramatic images. So we like to take pictures of nebulae. And now we can talk about star clusters. Here we have 2 images, for example, of globular clusters from the catalog, M5 and M54. And we see that these objects are basically composites of a lot of stars very, very close to each other. Tens of thousands to even millions of stars clustered together. In Hebrew, we would call them a tzvir or tzever, a cluster of many stars coming together or floating together in space. This kind of number, proximity, and masses would indicate that these stars are gravitationally bound to each other, which is why the shape is typically more or less spherical. It can get kind of amorphous coming out of the center of the sphere, but at least the core will be very spherical because of the gravitational forces binding the system together. And occasionally stars might get some kick and fly out, and other stars might fall in. But in general, the bulk of those tens of thousands, hundreds of thousands, or millions of stars will float around each other very, very closely around the sphere in a globular cluster. Because these systems are bound, they can be quite old and typically are very old. And as you recall, as stars age on the main sequence, they eventually run out of their nuclear fuel and go into the red giant branches and phases. So here we see for this globular cluster at the middle bottom, M5, we see an HR diagram, a Hertzsprung-Russell diagram for this stellar cluster. And we see that while it has kind of the parts of the main sequence around the sun are slightly redder than the sun, there are very few stars hotter than the sun or more massive than the sun, because those stars will have exhausted their hydrogen fuel and thus turned in what is called here TP, the tipping point, turn into the various red giant branches. So these kind of star clusters are typically a lot yellower and redder than just your random main sequence stars, which you can find in various masses. There's this gap here on the main sequence of slightly bluer stars, green and blue stars, which is missing from these old globular clusters. So we typically call these clusters, characterize them as being red and dead. So these are dead, many of them are dead stars, and they're hence much redder than your average main sequence star if you just pick a star at random from the galaxy. And we find these type of stars both on and off, or on or around the galactic disk in our galaxy. So if we kind of plot or trace where we find these globular clusters in the Milky Way, we see that many of them are huddled either on or just around the galactic disk. This is all in contrast to open clusters. Open clusters are much, much smaller. That is many fewer stars. Because there are so few stars, the mass is very low, and they tend to have more kinetic energy than binding potential energy. So they are not bound. They're actually free systems. These stars fly around each other and they feel each other, but they're not necessarily bound. They can be created in random or dispersed at random, which means they're typically much shorter lived, much younger, and hence a lot bluer. We see here a surplus of young blue stars as opposed to the redder and deader globular clusters. Pictured here is maybe the most famous open stellar cluster in the universe, or at least to humans, the Pleiades, which we already talked about in the second week of the semester. The Seven Sisters, or Subaru, one of the earliest stellar systems known to man, depicted here on the left on the Nebula disk from thousands of years ago. It appears in the Hebrew Bible. Very, very clear to see. And again, that is because the stars are far enough away from each other that you can make them out with your eye, at least the main ones, individually from each other. As we had mentioned before, there is no system of stars which are bound to each other, which we can tell apart with our eyes. These clusters are much closer to the galactic disk. So if the globular ones we see can mostly congregate around the center, but can also float above and below the galactic disk, these open clusters are much closer to the galactic disk itself. So those are two types of stellar clusters.
Can you explain the galactic disk? I mean, you say they are off the plane, the closed cluster. The first type of clusters?
Say that again?
The previous page of the slide?
This one?
Of the global cluster, yeah, you say they are not on the, they can be not on the galactic disk.
Yes.
But maybe I didn't understand what the galactic disk is, but shouldn't doesn't it, we know the Milky Way, we say it's not spherical, it's a discoid or a disk, and therefore if we see a star cluster, whether it will be a global or open, when we identify it to be of the Milky Way galaxy, doesn't it necessarily mean it's on the galactic disk?
So as we talked about in the last hour, Herschel identified that the galactic disk in the Milky Way, that the galaxy called the Milky Way, the first galaxy that we know of, has a shape of a disk. It's basically flat with some width. And so if we now look at the sky and we plot, we kind of project the sky around us in such a way that the plane of the disk is this line, this horizontal line in the center, then we can see various globular clusters and trace their position in the sky relative to the galactic disk. And we find that
okay, so it's a projection of the sky to a sphere, sort of. Yes.
It's a projection of the sky on a sphere. But
okay. So that's what
you can do that in many ways, right? Oh, you ask if the structure is spherical or if it's just a projection. This is just a projection.
Okay.
It's projecting the sky, so you have these kind of poles, which are the points in the sky perpendicular to the disk of the Milky Way, and you have latitudes and longitudes relative to the plane of the Milky Way. Okay. And that's where you find these globular clusters, mostly close to the center, but you can also find them floating around the galaxy, around the galactic disk, and above and below the galactic disk. And this study of globular clusters was really what gave the next step in showing that Herschel was wrong and that we are actually not at the center of the galaxy. So this is Harlow Shapley pictured on the right, a very important 20th century astrophysicist and astronomer. And what he did was kind of carry the Herschel methodology of tracing positions of stars around us, but he didn't do that to stars, he did that to globular clusters, 93 of them. And the reason you can do that is because these clusters each have, as we said, tens of thousands to millions of stars in them, which means they emit a lot more light. So you can see them further away. And when they are off of the galactic plane, they are also not dimmed as much as stars, because most of the dust and gas in the Milky Way is on the plane of the disk of the Milky Way. So it's a lot easier to see globular clusters far away and off of the disk. So you can both see them further away on the disk. They're brighter, and you can now study them in more parts of the electromagnetic spectrum. But you can also see them off the plane of the disk, which Herschel couldn't do at the time. And what Shapley found out was that contrary to the Herschel measurement of stars, which appeared to be symmetric around us on the plane, the globular clusters are not symmetrically distributed around us. There's a clear preference in this picture for globular clusters to be on the right side of our own position. And by plotting these various clusters, Shapley could infer from the again, assuming a distribution that's more or less symmetric, what the center of that symmetry would be. And it was no longer us, right? If you see these stellar clusters distributed, you might guess that the center of this galaxy is maybe somewhere around here. And then you'd be seeing kind of this wedge whose radii or whose spherical edge has a radius leading to some point on the right side, on the galactic plane, of course, on the disk, but far away from our own position. So this is exactly following Herschel's logic, but now following it with different data, not positions of stars, but positions of star clusters, globular clusters. And again, while the stars in our vicinity appear to be symmetric around us on the galactic plane, the globular clusters we can see much more far away and off of the galactic plane, and then we see that the symmetry is broken, and we can infer the real position of the center of the Milky Way, which today we estimate at about 26 kilo or 26,000 light years away from us, about 8 kiloparsecs away from us. So we are not at the center, we're 8,000 parsecs off center, out of a galactic diameter, which is about 50 kiloparsecs. At the time, they thought it was less. Now we can see more and more stars and even more dark matter in studies today. But we are about, I guess, around 8 kiloparsecs from the center, and the galaxy diameter extends even further beyond that. And as we said, Herschel got the answer wrong, not because his methodology or logic were flawed, but because the data wasn't good enough and couldn't be good enough at the time, because when you look in the plane of the Milky Way, your gas and dust blocks out a lot of the light, and he couldn't actually see stars farther than about 6,000 light years or 2 kiloparsecs away from us. On the distance scale of a few parsecs, of 1 or 2 parsecs, you might mistakenly think that you're at the center because it's symmetric around you, right? We're in a spiral arm. In the spiral arm, it's mostly symmetric around us as far as we can see. So you'd think that that's the entire galaxy, or he thought it was the entire galaxy. Now, when we can see farther, we realize that everything Herschel was plotting, all the stars he was tracing, were really just this little blob. This is here original on the right and here positioned on the left relative to the globular clusters. We can see that really he was just tracing a very, very small neighborhood, which he could see at the time, all basically within the local spiral arm, which is far from the galactic center. Okay, so this kind of ties together the Olber's paradox, or the understanding that the light you see is not all the light that there is. You do not see all the sources. Dust and gas are obstructing the light on the way. They're obstructing and dimming the light that you can see. And it's really going out to globular clusters and mapping them off the galactic plane and farther away, which allowed a better understanding of the shape of our own galaxy. Any questions thus far?
So Herschel only mapped a local cluster, and he thought it was the entire galaxy back then?
Yes, Herschel could only see the very local neighborhood, basically our own spiral arm, or some of our spiral arm, not even all of that, because the dust blocked stars further away. So we couldn't see further than the dust blocking.
Okay, and I was wondering if there are any free stars or only galaxies.
What do you mean free stars?
As in stars that do not belong to a galaxy.
So it's very hard to see things that are as far away as a different galaxy. If it were an individual star, it might be difficult to make out with a telescope. Sometimes we see these types of explosions as far as distant galaxies. But again, these might be difficult to pinpoint and also difficult on a theoretical level to explain how the star got there. Now, it might be that two galaxies collide, and then there's an imbalance in the gravitational binding potential and various things fly off, right? Like if you throw two balls against each other and they kind of break apart and you get a scatter of particles or stars flying away. So it's not impossible to have stars detached from a galaxy, but it's a lot harder to create a star just in random intergalactic space, because if you recall, what you need to create a star is a local mass density exceeding the gene's mass, and it's hard to get that mass close together just outside of any galaxy.
Okay, thank you.
But with clusters it's a little easier, right? You can see these globular clusters still bound by the Milky Way, of course, and they'll crash into it every once in a while because of gravity, but they can still float a while off. It's easier to see because there are, again, millions of stars in each. Okay, so Halo Shapley, as we said in 1917, established the shape of the galaxy as kind of composed of both matter, both stars and gas and dust, and understanding the obstructions that the gas and dust impose on what we see. But then the question was, okay, if we are not at the center of the galaxy, what does the galaxy look like, and what is there beyond the galaxy? Is there something beyond the galaxy, or is everything else just new things in our galaxy that we are yet to see and understand? And this prompted what is today called the Great Debate in astronomy and astrophysics. This happened just over 101 years ago, in April of 1920. It was an actual debate. The various scientists met together to discuss this question. It happened in Washington, D.C., in the US, at the Smithsonian National Museum. And the official question on the table was, what was the distance to what was then called the spiral nebula M31? That is object 31 on the Messier Catalog. Here's a picture available at the time from 1899, the Andromeda Nebula, because it's in the galaxy, in the constellation of Andromeda. And they noticed, of course, the shape. They noticed it was spiral. It also had this kind of nebulous appearance. You see these kind of dust clouds or gas, these nebulous cloudy shape at the edges, but you can start seeing the spiral arms as well. At least you can see maybe one going out here, another one going out here. They kind of realized that the structure of this was not just a typical nebula that was maybe more amorphous. This nebula, what they called a nebula, was quite flat. It was disc-shaped, and it had these kind of spiral arms to it. So it looked weird. And they asked what it was, the nature of this nebula, and how far away it was. Those two questions are related, of course. If it's a nebula that's emitting a lot of light, maybe from a lot of star formation, maybe something else, maybe it's farther away and bright, maybe it's closer, and then it's not so difficult to understand all this light coming out of it. There were basically two sides to the debate. One was presented by the same Halo Shapley himself, who discovered the structure of the galaxy, and he claimed that this M31 object was a nebula inside the Milky Way. It's another object in the Milky Way, like the globular clusters that he traced following around and orbiting around the Milky Way. And he had several reasons. One of them was that if it's an external object, it would have to be very, very far away. It would have to be about order of 100 million light years away. Because again, the galaxy itself, our galaxy, they realized was quite large, tens of thousands or 100,000 light years. And this would have to be even further away to appear to us as it does. And that is very, very strange, very, very far away, farther than they thought something like that would be possible. Also because they found a nova, a sudden brightening of a new star, basically, in M31, similar to, I think we talked about novae actually, right? A neutron star or a white dwarf, which accumulates matter. That matter is ignited and suddenly becomes bright. So they knew about novae at the time, and a nova was found in M31, which was brighter than the entire nebula. So just a point of light in this nebula, which outshines the entire nebula. And if you consider that this object is 100 million light years away, and that a single star or a single event can outshine the whole thing at 100 million light years away, that's very, 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 very strange. Impossible at the time to think of what would be so energetic to outshine a full nebula, or today we would say to outshine a full galaxy. So that was an argument against this being far away. If it's closer, then it's easier to explain. It's a local object, and there's a nova in it, which is maybe maybe somewhat bright. It's as bright as a full nebula, but not as a full galaxy way off in the distance. Also, another Messier Catalog object, M101, is another spiral nebula. And for that, there was a measurement of the rotation velocities. And if you measure the rotation velocity, then you can, from the distance, try to estimate the distance. And if the distance is out of the galaxy, then that means the size has to be very, very big for us to have the same angular diameter as we see in the sky. And if you calculate the rotation velocity measured by the distance from us, it would have to travel faster than the speed of light. It would have to rotate faster than the speed of light, which at the time was already beginning to be established as impossible. So Shapley had a few arguments about why these spiral nebula cannot be as far away as outside of our galaxy. They have to be these strange looking, but minor objects inside our own galaxy. On the other hand, was Curtis, it's the Shapley-Curtis debate. And Curtis said, no, this object is not in our galaxy. It's a distant galaxy, it's a separate galaxy. The Milky Way is really not the only Milky Way that there is. The galaxy can no longer be described as a single object in the sky on which we sit. It's just one of many galaxies, and this is obviously, to him, a distinct separate one. And his reasons, also good, were that there was not just this one nova in M31 outshining the nebula. There were actually a lot of novae observed in M31. Actually, in this single object in the sky, this single nebula, there were more novae observed than in the entire Milky Way. And it's, again, very strange if we have a little part of our galaxy with more fantastic events happening in it than in the whole rest of the galaxy. That's kind of weird. It's very, very not unusual. However, these other novae were not just more numerous, they were also a lot weaker than the ones that we measure from the Milky Way, the other ones. About 10 magnitudes weaker, and if you recall, a factor of 5 in magnitude is a factor of 100 in brightness. So these are 10 magnitudes means a factor of 10,000 less bright than the novae we see in our own Milky Way. So why would this little patch of the galaxy have more events and all of them a lot weaker than the ones we are used to? It makes more sense if this object is in fact a separate galaxy, and then we're just seeing the average number of novae per galaxy, but farther away, and so weaker. The third argument was that these dust lanes in the Andromeda Nebula look very similar to the ones in our own Milky Way galaxy. So we have an object here that maybe should be understood as a separate galaxy like our own. Any questions about the debate, the question, the answers, the arguments? Okay, so what's the answer? The answer was given by Edwin Hubble, pictured here on the right, whom today we all know from the Hubble Space Telescope, named after him. And what Hubble did was not immediately, it took a few years, but eventually gave the final answer that decided the debate, that determined the correct answer. And what he did was directly measure the distance to the Andromeda Nebula. And what he did was basically use Cepheid variable stars. We talked about them when we talked about variable stars earlier on in the semester. Henrietta Swan-Leavitt, as you recall, gave a formula estimating or relating the absolute luminosity, the absolute magnitude of a star, of a Cepheid variable, to its period. And then if you know the observed magnitude and compare it to the absolute magnitude, which you can estimate from the period, you know the distance. And this is what Hubble did. He used the Swan-Leavitt formula and estimated the distance of just under 1 million light years to the Andromeda galaxy, the nebula, after which the galaxy, about 900,000 light years away. Today we think it's about twice as far. It's about 2 million light years away. But this was the first time. A factor 2 is not too bad in astronomy, and for him, this was the decisive evidence. He found 3 Cepheid variables in M31 and in other extragalactic nebula, as they were known at the time, and he showed that if the galaxy is only a few 100,000, or at the time less than 100,000 light years across, then this object, about 1 million light years away, has to be a separate galaxy. And so henceforth, the M31 is no longer a nebula, it's now considered a galaxy. And Hubble proved basically that there are other galaxies in the universe in addition to our own. Any questions?
Was this the first galaxy seen besides ours?
I don't know what you mean by seen. It was the first one proven to be a galaxy. But if we go back to the Messier Catalog, recall this is like end of the 18th century, and it has many objects which we now understand are galaxies. Right? So there's M31, 33, 74, here 99 to 102, 106, 66, many galaxies. And these were all seen by telescopes long before they were understood to be separate galaxies. What Hubble proved was that these types of spiral nebula or unknown objects in the Messier Catalog, and by his time we had many more of them observed, were in fact separate galaxies. So Shapley established the shape of our own galaxy. He got the M31 question wrong, but then Hubble corrected or used that, built on that, corrected the distance estimate, and prove that all these other objects were in fact separate galaxies. Now, of course, if you look at this image again, you can see another galaxy in it, right? Here on the top right, there's another galaxy. So we are, and this is again an 1899 picture. So today we know of hundreds of millions of galaxies in the universe, or estimate their number to be something like that, and we know a very great number of galaxies in the universe. Okay, we should also correct, explain a bit about Shapley's arguments, because the logic again was sound. In this case, some of the data was missing or wrong. The rotation velocity of M101 was remeasured after that, and it was found to be much lower than Shapley expected, or that Shapley relied on. So nothing actually breaks the speed of light. It was just a mistaken measurement. And the nova, the so-called nova in M31, outshining the whole galaxy, was in fact not just a regular nova. It was what we today call a supernova. And in fact, supernovae, as we'll see next week when we talk about explosions, can produce as much luminosity for a brief time as an entire galaxy, outshining a full galaxy. So at the time, it was considered improbable to the point of disbelieving a separate galaxy. Today, we know also based on Hubble that if something in fact is in a separate galaxy and outshines the whole galaxy, it cannot be a standard nova. It's in fact a supernova, a whole new class of stellar explosive phenomena. Okay, so how do we understand our galaxy today and its structure? Of course, this picture here on the right is not the Milky Way and cannot be the Milky Way because we don't have a picture of the Milky Way taken from outside, but it represents what the Milky Way looks like based on a reconstruction or a projection of the stars we see in the sky and the objects that we see. So the Milky Way is a barred spiral galaxy. It's a large spiral galaxy, and it has a bar in the middle. So we have here spiral arms. In the Milky Way, various spiral arms have names. So there's the Sagittarius arm, the Scutum Centaurus arm, the Perseus arm. They are, of course, named after the constellations in which direction they appear. To us, the center of the Milky Way, to us, appears to be in the sky direction of Sagittarius. The center of the Milky Way, as we said, hosts a black hole. That black hole is called Sagittarius A star. It's the largest in that direction in our galaxy. We can see on top here that our solar system is again off center. It's in one of the spiral arms, the Orion spur, to be exact. It's on the side, and the direction of the ecliptic plane, that is the rotation of the Earth and other planets around the sun, is not along the galactic plane. There's an angle between. So we have kind of this nice view of the galaxy without having to always look through the sun. So now we have kind of three important planes in astronomy. Of course, the equatorial plane of the Earth, perpendicular to the Earth's rotation, the ecliptic plane, and now the galactic plane, which will be our reference plane for any measurement done, or any measurements and descriptions of other objects in the galaxy. On the galactic plane, we measure angles from the axis, the longitudinal axis leading from connecting the sun to the center of the galaxy. And then we can describe any position on the Milky Way, either relative to the center or relative to us on the galactic plane with an angle relative to the direction connecting us to the center. Of course, that's on the plane. Off the plane, you'd add a z-axis perpendicular going outside of the galactic plane. There's a typo here in the second line. Our galaxy has between 100 and 300 billion stars. so about 10 to the 11, or order of 10 to the 11 stars. Sagittarius A star, as we mentioned, 4.6 million solar mass black hole at the center. The galaxy rotates. It doesn't rotate at the same velocity everywhere. It's not a rigid body. Our sun, at the position or the radius of our sun, we rotate at about 220 kilometers per second around the galactic center. The full radius of the Milky Way is not exactly the same everywhere, but we estimate it between about 75,000 to 200,000 light years. So that's between about 30 kiloparsec to about 60 kiloparsec, something like that. This is only the stars, or what we see as baryonic matter. There's a dark matter halo. We'll talk about dark matter in 2 weeks, but there's dark matter halo established in the last few decades to surround the Milky Way, and that extends up to 1 million light years away from the center. At our radial distance from the center and at our current rotation velocity, which is not expected to change much, we expect to circle the Milky Way every about 240 million years. We think today that the age of the Milky Way is about 13.6 billion years, which means our sun has actually completed multiple rotations around the galactic center. And some people think that's important for phenomena on Earth on very, very long timescales of hundreds of millions of years. The galaxy is actually quite old. It's only 200 million years younger than the universe itself, more or less to the accuracy that we know. So the galaxy actually formed a very long time ago. Our sun, as you might recall, is less than 5 billion years old. The Earth is about 4.6 billion years old. So in our case, the Milky Way has been around for a lot longer than our particular solar system, which is quite new. And we are not alone in the sense that the Milky Way is not a single galaxy floating in space. It's part of what's called the local group of galaxies, which includes galaxies like Andromeda, M31, our very close neighbor and partner, and a very similar galaxy to our own, and other galaxies as well in the local group. The local group itself is part of the Virgo supercluster of galaxies, which itself is now part of what was only established in the last few years, the Laniakea supercluster, or supercluster of galaxies. This is kind of showing the different components of the Milky Way, thinking about them in a different way. We talked about the galactic disk, which is thin around the galactic center. The galactic center is not flat. There's a bulge. It's a more spherical bulge at the center of the galaxy. Around it, there's a rather thin disk. Around it, there's a part of a thick disk and the halo. And the halo, as we mentioned, contains things like globular clusters, which are found mostly in the halo. And we can compare here between different parts of the galaxy. In terms of stellar mass, the thin disk is the prominent one. Most of the mass of the galaxy in stars is in the thin disk, about 4 times as much as the stellar halo surrounding the galactic plane. The thick disk itself is quite small. It is interesting, though, that the thick disk, for example, typically has very old stars, similar to the halo, where we said we have globular clusters and typically red and dead stars. So they're quite old, as opposed to the thin disk on which we are located, where stars can be quite young, so much bluer and younger than the other parts of the galaxy. Today we associate that, or we conclude from this, that star formation takes place on the disk and not off of the disk. So the younger components of the galaxy, the young stars, were formed and are still being formed on the thin disk of the galactic plane. This is related to the fact that heavier elements are more prominent on the disk, of course, where stars are younger, than in the thick disk and halo, where the stars are older, so they are older population stars. When they formed, there was not so much heavy elements floating around yet. Okay, we talked about the effects of dust and gas on what the galaxy looks like in visible light. Basically, the dust lanes obscure the next spiral arms or the stars far away from us. And here we can see an example of that. In visible light, the galaxy looks just like it would if you looked at the night sky from someplace far from the city. If you went to the Negev desert or somewhere, and looked in the sky, this is basically what you would see. You would see dark lanes, dust lanes, and some light coming on scattered from around it. Infrared, there's a lot less scatter, and so you can see a lot more of the galactic plane showing off. You don't see the dust anymore. You can see through the dust, and you can see this red disk of the galactic plane. In many other ways to look at the galaxy, we can see, again, so this is the IR, which we saw before in a slightly different rendering. You can see the red disk in either near IR, which is closer to visible light, or deep IR, and in high energy. So you can see the gamma ray plane of the disk. You can see the X-ray structure of our disk, of our galaxy. Interestingly, you can see a few sources in gamma ray in the galaxy, which are as bright as the full center of the disk. So the Vela pulsar, the Crab pulsar. The Crab pulsar is the center of the M1 Crab Nebula in the constellation of Crab. Geminga pulsar, these bright yellow objects are very, very bright in gamma rays. We might talk about them a little more next week. In X-rays also you see exceptional regions off the plane where X-ray is very strong X-ray sources. You can also see both in radio and in X-ray, these features coming out of the center of the galaxy, basically out of the central black hole. And the region of the central black hole with its accretion is a very, very strong source of both X-ray and radio radiation emissions coming out of the center of the galaxy. This is now already approaching the kind of the realm of high energy astrophysics with X-ray, gamma, radio, and other sources. Okay, looking a little closer here in X-rays, we can see some of the same famous sources. Again, the Vela pulsar, the Crab pulsar, and other pulsars, another black hole, Cygnus X1, supernovae remnants, which we can find as strong X-ray emitters. We can also see a few other galaxies, like the Large Magellanic Cloud, which is a satellite galaxy to our own, and parts of the Virgo cluster and superclusters, and again, other galaxies and other clusters of galaxies in our vicinity. And again, what's called the North Polar Spur in X-ray, this cloud or region of excess X-ray emission coming out of the center of our galaxy. So this is a color rendered X-ray picture of of the sky around us. In all of them, of course, the galactic plane is the most prominent feature. Okay, the spiral arms should be explained where they come from. And one of the explanations today is that, in fact, it's not that the galaxy is empty, between spiral arms. The galaxy the galactic disk is full, basically. It's all matter, gas, dust, and other things. But the rotation of the galaxy creates density waves going outwards. So you start with spherical symmetry, not spherical, disk symmetry. So rotational symmetry or helical symmetry. But the rotation creates these density waves going out. Whenever you get an overdensity at some point or at some radius, that overdensity can locally surpass the Jeans mass. And if you locally surpass the Jeans mass, then you trigger a collapse and a new star is born. If a new star is born, it starts emitting light, it emits wind, which clears away some of the dust and gas around it. And so what we're actually seeing is not where there is more matter or less matter, but where there is more star formation or less star formation. So what we're basically tracing are these density waves coming from the rotation of the galaxy. And whenever a density wave triggers star formation someplace, we'll get a burst of young blue stars. And that's really explaining why the galactic plane is the place to look for young blue stars. It's because that is where star formation can occur. While off the galactic plane, you'll find old red and dead stars, globular clusters, which are older, basically stars which formed a long, long time ago. But the young ones, the population 1 stars, the heavy element rich stars will be forming on these, what looks to be the spiral arms, but are really the result of density waves. And I think Yehu will give you a homework exercise exactly on this topic. Okay, just a few more words on the galactic center before we take a break. As we already said last week, or as we saw in these slides, there's a very strong emission of high energy and microwave from the galactic center. If we look at it, again, not in visible light, that's blocked by dust, but in other wavelengths, we can see all of these various Sagittarius constructs. Again, it's the constellation of Sagittarius. We can see supernova remnants. We can see different arcs. We can see this kind of excess radiation coming from the center. And of course, the very, very bright object at the center of the galaxy, Sagittarius A star, which today we understand from other observations here in near infrared to be a black hole, a supermassive black hole. In this image on the right, we don't see Sagittarius A star. It doesn't emit that much near IR, but we can trace stars traveling around it. We can trace stars orbiting the center of the galaxy. And as we talked about last week, it was this 30-year follow-up of orbits around the center of the galaxy, which established that there was a very massive black hole at the center, which we cannot see directly, but whose mass effect on the orbits around it, we can trace and find. So our galaxy has a massive black hole at the center. And today we believe that actually every galaxy has a very massive, supermassive black hole at the center. Okay, that's probably a good place to stop until we talk about other galaxies. So let's reconvene at 2:05 and discuss other galaxies. Any questions?
Mofek?
Yes.
What we see when we analyze our own galaxy, we see one of the other arms, right? We see an arm, and after the arm, we see the center, which is covered by the arm.
When we look?
Yeah.
So if we go back here, you can see that we actually see maybe a few spurs, like maybe our own spur, another spur over, then the massive Scutum Centaurus arm, then maybe a weaker, a smaller arm, and then we can kind of reach the bulge of stars in the center, and then the black hole.
Mm-hmm.
And what this means, of course, is that it's actually very hard to look into the center of our own galaxy, because you have spiral arms and dust lanes, and a lot of things obstruct the view to the center of our own galaxy, which is why the famous picture of the black hole, the Event Horizon Telescope picture, is not of the black hole in the center of our own galaxy, which is the closest supermassive black hole to us, but actually M87, another galaxy far away, well, not very far away, but not our own galaxy, just because it's positioned off the plane of our own galaxy. So basically nothing obscures the way. It's easier from our galactic perspective to see centers of other galaxies more than we can see the center of our own.
I see. I was wondering if we wouldn't have those things blocking, like the two spiral arms or three blocking the center, would we be able to see with visible light the crescent disk and the effects of the supermassive black hole? Because it should be a pretty radiant and massive if nothing would cover it.
So you need, first of all, to remove the galaxy, right? The spiral arms, the dust lanes, the disk. You need to remove everything that obscures visible light. And then you have to ask if the black hole is even emitting, or if its environment is emitting visible light. And it's easier in this case to see the X-ray, to see the near IR, to see other frequencies from the center of the black hole, which are not scattered or blocked as much.
Okay. Thank you.
We do have a promise from the Event Horizon Telescope that they will release a picture of kind of our own black hole, supermassive black hole, but we're still waiting on that to happen.
Good luck.
Thank you. Let's all wish them good luck.
Yep.
So after discussing the existence and structure of our own galaxy and demonstrating that there are other galaxies, now we can talk about what those galaxies are and how we try to get more information or understanding about them. So shown here are a couple of pictures. The right one is from the Hubble Space Telescope. It's called the Hubble Deep Field, which means the telescope is not pointed at a particular star that we know of in our galaxy, but just kind of out there. And what we see in this deep field image from Hubble, the telescope, not the person, is of course many, many, many galaxies. Basically, as many galaxies out there in the universe as stars in the night sky, if you were to look at the near field. Hundreds of millions of galaxies are out there. On the left here, we have an image from the Sloan Digital Sky Survey, another important source today, mapping out and classifying different galaxies in the universe, a lot of them. And so just as Hertzsprung and Russell classified stars in the beginning of the century analyze stars according to classifications developed at Harvard at the end of the 19th century, there was also a catalog made for galaxies, for mapping out other galaxies. The first one was called the Shapley-Ames catalog. Shapley we already talked about. Adelaide Ames is pictured here on the right. And they were and that was a catalog basically trying to explain different types of galaxies and give some order so they won't all be in the same category. We can see some features and understand them a little better. For example, under the Hubble classification, recorded here on the left, there was this distinction between at least three types of galaxies: spiral galaxies, like our own Milky Way, like Andromeda. These spiral galaxies can either have a bar in the middle or not have a bar at the center. and elliptical galaxies on the left. It looks like this type of tuning fork form because they thought at the time it was some sort of evolutionary process. But basically it goes from the ellipticals from 0 to 9 grow in the ellipticity. So from basically spherical to more and more elongated and clear shape of an elliptical galaxy. And the spirals as well have the classification of 0, A, B, and C based on the clarity and complexity of the spiral arms, with the possible B indicating a bar in the middle. At the end, we have irregular galaxies. Those also exist, galaxies whose shape doesn't fall neatly into any other category. These early classifications were developed into what's more common today, the Hubble-Divac-Coulomb diagram, or the tuning fork diagram. It looks like a series of ellipticals, again, growing in shape from spherical to sharp ellipse. Then we have the lenticular galaxies. Lenticular is lens-like, or a dasha, a shape of a lens, breaking off into the spirals, here shown more clearly, and again, growing complexity of the spiral arms. These are the A galaxies. Intermediate, which are starting to develop some sort of a bar, and the barred spirals, which have a very clear bar in the middle, the barred spiral galaxies. And again, on the right side, we have different types of irregulars, which don't fit the other classifications. But these are the main categories of galaxies we classify today, between ellipticals, spirals, intermediate or barred spirals, or irregulars. Surveying many galaxies, we can learn something about their characteristics or typical parameters. For example, in mass, we see that the spirals are rather narrow in range, from 1 billion to 1 trillion or 1,000 billion of solar masses, while the ellipticals have a much wider range, even as small as 100 million solar masses, and can be up to as big as large as 10 trillion solar masses. Similarly, in diameter, spirals are typically around 1 order of magnitude, from 15 to 150 kilo or thousand of light years. So from basically 5 to 50 kiloparsecs in diameter, while the ellipticals have a much wider range. And similarly for luminosity, the spirals being more narrow and the ellipticals being wider in range of luminosity. More interesting maybe is the types of stellar populations, where the ellipticals mostly have older stars and spirals have both old and young. And we already discussed that the young stars appear in spiral galaxies because the rotation itself, creating the spiral arms, triggers star formation and makes a constant production of young stars, young blue stars in these spiral galaxies. Okay, we can also analyze slightly more complicated features like the mass to light ratio, that is how much mass per given luminosity, at least in the visible part. And this relation will help us know how to expect, or how much light to expect from a galaxy, or vice versa, how much mass to expect from a galaxy based on the amount of light that it produces, either for the visible part or for the total part of the galaxy that includes the dark matter, which we do not see. This relation between mass and light can help us, because mass is something that we can indirectly measure for a galaxy. We can measure it indirectly from the velocity of rotation of the galaxy, again by Kepler's law or by Newton's laws or by some approximation of those. If we know what the velocity is, which we can measure from Doppler shifts for example, by looking at a particular line that we know of, the Doppler, the 21 centimeter line from neutral hydrogen, we can measure that line and see how much it splits or broadens, and that will give us the velocity dispersion. That is, what is the velocity difference between the part of the galaxy rotating away from us and rotating towards us. And that, so we can know the distance from the center of the galaxy and the velocity of the rotation. And the velocity of the galactic disk will tell us or give us a hint about the mass of the galaxy, the total mass of the galaxy. If then we use this relation between total mass and absolute brightness or absolute magnitude, like the one that's presented here on the right, then if we see the velocity, we can estimate the mass, plot it here on the bottom, or rather indirectly plot the velocity on the left and guess the absolute magnitude on the x-axis. So basically we measure these as best as we can for some number of galaxies, spiral, lenticular, elliptical, or whichever type of galaxy. And we see that there's generally a relation. Generally, the magnitude will increase, or the magnitude will be brighter as the velocity grows. So faster velocity will be higher mass, and that will determine some linear approximation of this ratio of magnitude to brightness. What that then means is that if we measure an observed magnitude, small m, from the small m observed magnitude and the expected absolute magnitude, capital M, which we infer from the measured velocity v, we can measure or estimate the distance to the galaxy. Okay, this is again very similar to how we would do for a star. If we know the color or temperature of the star, we know what the flux should be. That gives us the absolute magnitude. If we then measure the observed magnitude, comparing them gives us the distance to that star. So in this case, the distance is not to a star, it's to a galaxy. And the estimate for the flux from the luminosity of the entire galaxy comes from these type of relations between velocity or mass to the expected magnitude or brightness. And these are called Tully-Fisher relations, based on those two astronomers or astrophysicists from the last few decades. And this again extends our ability to measure things very far away. You have no a priori way of knowing how far a galaxy is. But if you can calibrate this relation based on nearby galaxies, whose distance you do know from other means, for example, supernovae, Cepheid variables, our LIRA variables, any other type of calibrating the distance, then now if you see a galaxy far away, just by the velocity dispersion and by the observed magnitude, you can get an estimate of how far the galaxy is. Okay, so now we can map the distance to faraway galaxies. And these types of mappings give us a way to kind of map out the local group, which we mentioned. So here is our own galaxy, the Milky Way, at the bottom right. Our Milky Way has a few satellite galaxies, which orbit the Milky Way just like planets orbit a sun. Most famous of these are the Small and Large Magellanic Clouds, again, discovered as clouds or nebula by the crew of Magellan in the early 16th century as they passed through the Magellanic Straits, circumventing the Earth in South America, around South America. They cannot be seen from the northern hemisphere, but they are very clear from the southern hemisphere of the Earth. They are actually known today not to be clouds or nebulae, but to be distinct galaxies, smaller ones, but nearby, our closest satellite galaxies. And many, many more galaxies which kind of surround or orbit us, Barnard's galaxy, and others. Our most important neighbor is the Andromeda galaxy, M31, which is roughly the same size, about 2 or 2.1 million light years away. Seen here in the same picture that we used before, or a modern picture of the same galaxy. And Andromeda has its own satellite galaxies, like M32, the Triangulum galaxy, and many, many other galaxies orbiting in the local group, orbiting Andromeda. And of course, by being a local group, the Milky Way and Andromeda are locked gravitationally, or bound gravitationally. We can never be too far apart, and eventually, in many billions of years, we expect Andromeda and the Milky Way to crash into each other and to merge. Eventually, the entire local group will, at some point, merge into a single galaxy, a massive galaxy. This is something that happens. Galaxies do merge. Here on the right, we have actual images from the Hubble Space Telescope, not of the same pair of galaxies, because obviously two galaxies crashing together is a process that takes billions of years, or hundreds of millions and billions of years. But we have enough galaxies in the universe to be able to get these kind of sequence or various snapshots in time of many, many types of collisions between pairs of galaxies. And we always see kind of a galaxy crashing into another, arms getting flung out by the tidal force the galaxy exerts, one of them exerts on the other, these tails going out in different directions. Here in the bottom right, we see two galaxies really as they're kind of both looking to us head on and merging. And something similar is expected with Andromeda. Here on the left is a kind of an artist's description of what this might look like to viewers on the Earth. Again, in a very, very long time. At first, you'll see the Andromeda galaxy kind of approaching the Milky Way in the sky. And then as they start to disturb each other gravitationally, we get a big mess of stars and gas floating around. The overdensity coming from two galaxies merging will create a new period of star formation. And so we'll have a lot more blue stars in the sky. Young stars will start filling up the night sky. And eventually they will kind of coalesce into a final joint galaxy, which we might see in the sky, either something inside, either we are inside of it or just outside, as either the sky all around us or some sphere, or again, just some new plane of the galaxy. The future of the night sky of the Earth, if we survive long enough until then. Okay, as I said also, the local group is part of the Virgo supercluster, which itself is part of the Laniakea supercluster. So this here in blue in the middle is our local group, basically Andromeda, the Milky Way, and our satellite galaxies, part of the Virgo supercluster, which itself is joined by other superclusters around us to form this kind of, to start building this kind of a web structure or network of galactic clusters and superclusters connecting to each other on a larger and larger scale. We show it here with the stars, but of course on these scales, it's the dark matter that really determines the structure, much more importantly than the stars. This is kind of an artist's description. This is numerical simulation and cosmology trying to follow the evolution of the universe and its dark matter. And it has this tendency to form these webs called the cosmic web. And whenever these strings kind of meet, there's an overdensity and you get galactic clusters and superclusters form. So this is what the universe looks like on the grandest of scales, the cosmic web and the galaxies forming on top of it. Any questions? Okay. So the last topic for today is talking about energetic sources from other galaxies, or specifically about quasars, or what used to be called quasars, quasi-stellar objects, and today are realized to be active galactic nuclei, or AGNs. So this topic also starts with a mystery, as everything does in astronomy and astrophysics. It starts with an observation that we don't know how to explain. In this case, we have an image on the left side, on the left bottom, of two objects close to each other, or on the sky they appear close to each other, except that the right one is a star nearby, and we can analyze the star by analyzing the spectrum, looking for the familiar spectral lines of various elements, calculating the temperature and doing all those measurements that we know, and realize that it's in fact a star. Just on its left is something that looks like a star, and so was called a quasi-star, quasi-stellar object, or quasar. But in a telescope, in a visible telescope, it looks just like a star. But then the spectroscopy shows that it can't be a star. It's redshifted by a very, very large amount, tens of percent, it would be 10 to almost 50% redshift, which would be impossible for a nearby star. It would have, that means it has to be traveling at a large fraction, approaching the speed of light away from us, to be redshifted by that much. So it can't be a nearby star. And in fact, it can't just be a faraway star, because if something emits light like a star, the luminosity of a star, and it's so far away, we wouldn't see it at all. The brightness would be too low. To look like a star and be as far away as billions of light years, it basically has to be with the luminosity close to a full galaxy, or fractions of the luminosity of a galaxy. And that basically means it has to have a fraction of the mass of a galaxy. So these were kind of realized that they had to be, these quasi-stellar objects are actually kind of galactic in scale. On the right here, we have an example of just how redshifted these spectra can be. This is, I think, almost a 50% shift. If you look, for example, at the magnesium-2 line, typical line from once ionized magnesium, you can see that it can move from about 700 nanometers all the way to something like 400 and 450. So almost, maybe this is 30 or 40% in redshift. And similarly, an oxygen line, oxygen-3, so twice ionized oxygen, can move from something like 800 to around 500 nanometers. So we do follow the same spectral lines, but shifted by a large amount. So it's a very safe measurement, or a reliable measurement. And again, it indicates that these objects have to be very, very far away to be redshifted by such a great amount. And that also means that they have to be very, very massive to produce so much energy. So what are they then? So looking at them closer with telescopes now, we can often find a galaxy surrounding these quasars, these quasi-stellar objects. For example, and this is our favorite quasar, and today, these days, our favorite active galactic nuclei and favorite black hole, M87. The galaxy M87, if you look at the center, you can find this, you can see both the galaxy and the object, the bright object at the center of the galaxy. Do I have the scale here? I don't think, maybe I'll have them in the next slide. We can see the galaxy, so we can make a redshift measurement, not only of the whole galaxy's motion, but of the different sides of the galaxy. We can see the blue shift on the part of the galaxy that's approaching us, and the red shift on the part of the galaxy that's receding or moving away from us. So that can give us a measurement of the velocity of rotation of the galaxy. And we can see the splitting for the rotation, we can understand that this, in fact, is a separate galaxy far away from us. We can measure it. We can do the estimate the galaxy's velocity by Hubble's law, which we'll talk about in 2 weeks about cosmology. And we can see that this is, in fact, a supermassive, super bright object at the center of a different galaxy. And we can see that it could be as bright as a galaxy. And the way we understand it is that there's a supermassive black hole, and the black hole is accreting matter. It's swallowing up matter from stars that were too unfortunate to pass by, ripped apart, tidally disrupted. Then they feed all their matter to an accretion disk surrounding the black hole. As this disk kind of narrows down and circles around the black hole, the inner part falls into the black hole. The outer part gets dynamically, has dynamical friction with the inner parts. That is, you have a disk. If it's Keplerian, then the inner part moves fast, the outer part moves more slowly. If you have differential rotation, the fast-moving part is pulling the slow-moving part, and vice versa. The slow-moving part is pulling the fast-moving part. That creates friction. It means that the outer part is being accelerated by the inner part, and the inner part is being slowed down by the outer part. So energy is flowing from inside to outside. Both energy and angular momentum are flowing outwards. And that's basically a way of converting the gravitational potential energy deep, close to the black hole, or around the isco of the black hole, moving it outwards in the disk, heating up the inner part of the disk out of the isco. The disk heats up a lot, and as it heats up, it radiates a lot of energy. So we have an accretion disk, and it radiates a lot. There's also a jet coming from closer to the center, related to spewing out both radiation, high energy radiation, and very energetic matter. These jets can be, because they're very fast, they're relativistic, they will typically be beamed to a very, very narrow direction. And we see this. We see this again at M87. We see the center, the AGN, and we see in various types of telescopes, the jet coming out of the center, kind of flowing outwards and emitting a lot of energy, radiation, and matter, very, very fast, very hot, basically into intergalactic space. Here on the left, we see, again, a picture similar to the one that we saw with the galactic plane of our own Milky Way. Again, we cannot see the center directly in visible light, so we have here a visible image just of the dust lanes. But we see that there are these bubbles above and below the center of our own galaxy, extending as far as 25 or so thousand light years up and down. And from these bubbles, we have both X-ray emission and gamma ray emission. And these are kind of coming right out of the vicinity of the black hole in the center of our own Milky Way. On the right here, we have another example, the elliptical galaxy NGC 4261. And we have here a breadth of about 90,000 light years to the side, and about a similar direction to the top, energy being emitted in very, very strong jets going up and down. And if you zoom in on the center, then you can see really this kind of bright source at the center of that galaxy. So we today associate all these AGNs, these active galactic nuclei, to supermassive black holes in a very, very hot and dense environment, which are accreting matter, accumulating matter, heating it up, and emitting a lot of radiation, both thermally all around, and specifically in jets outside of the plane of the orbits around it, or the disk around that central black hole. So that's the Milky Way, NGC 4261, and here on the bottom we have our favorite M87, with the center being launching these jets of energy outside. Okay, I think we're actually done on time for a change. Any questions about galaxies? Galaxies, clusters of galaxies, stellar clusters, galaxy clusters, superstructure, AGNs.
The quasars part?
The what?
Quasars?
Quasars, yes. Quasars.
The quasars part, isn't it just like centers of galaxies? Why is it a different phenomena between galaxies if we speak of the centers of the galaxies? If you will understand my question.
So not all galaxies have to have an active center. For example, if you don't have a black hole at the center, the galaxy would not be bright at the center. It would just be a bunch of stars. But stars emit radiation slowly over a very long time. It won't create such high energy or such powerful energy emissions. Mm-hmm. It would basically look like the visible, right? You'd see the center of the galaxy would be slightly brighter than the outskirts, like you see in this picture behind me, but nothing very, very bright. Another way is to have a black hole that's not accreting. If it's a black hole that was there for a very long time, but it cleared off all of its environment, then it would not be accreting, and it would be, again, kind of a dormant black hole. To produce an active galactic nuclei, you really need to rip a star apart, feed it into a black hole, and then release not just the fractions of percent of energy contained in a star in nuclear burning, right? We saw for the sun that you can only release a small part, right? In our sun, I remind you, a proton is about 1,000 giga-electron volts, or 900 giga-electron volts in mass. Converting it to a neutron releases about 7 mega-electron volts. So that's like 1 in 10,000 of the mass, or 1,000th of a percent of the energy in the matter is released in the nuclear process. But when you throw something into a black hole, rip it apart, and it comes down and it releases gravitational energy, it can go up to actual percentages or tens of percentages of percent of its rest mass being released as gravitational energy. So you have like a factor of 1,000 in the efficiency of the process and the amount of energy you can release. So black hole accreting matter is a lot more energetic than just a star burning fuel. So and if you have an active galactic nuclei, then if you have a black hole that's accreting stars and really kind of you're feeding in stars and releasing much, or maybe not most, but maybe 10 or 20% of their energy, of the rest mass energy outside, then it's a much more massive, much more energetic source. And then it would actually be a considerable amount of the energy coming from the galaxy will be called an active galactic nucleus. There's a factor of 1,000 in the efficiency of energy release.
Okay, thank you.
Okay, any more questions?
Yes, I do. I have. Maybe you said it, but maybe I wasn't listening. But the quasars, the jets, are they visible? I mean, are they in the visible range?
It depends. So for example, here you see M87, and you see here we have a visible image. This is Hubble Space Telescope, and even
this is like this is non-filtered.
I don't know what you mean by filtered.
I mean, it's in the visible range between 400 and 700 nanometers.
Yes, this is visible light.
Yeah. Okay.
I'm not. It's not indicating that the actual color is pink. This is probably integrated over all of the visible spectrum, or I guess much of the visible spectrum. But yes, you can see it in visible light with a very strong space telescope like Hubble.
And what causes it to be this shape, the jets?
Usually it's a combination
specifically on one.
Oh, why it's one-sided?
On one axis, yeah.
That's
one axis, question. Yeah.
It's a good, no, there's a difference between one axis, like this here, NGC 4261. There's one axis, but two directions. That's
that's what I meant, the plus side and the negative side.
Oh, that's more common because if you have symmetry, if you have some rotational symmetry, then you have a disk and you have the axis. And typically the magnetic fields and the emission will be, even for symmetry reasons, more or less in the direction of the axis. And because the energy is very high, then you'll have relativistic beaming. So things that are kind of far away will be beamed to a very narrow jet. It's a Lorentz contraction from high relativistic velocity. So space can contract in one direction, but not in the other. So the angles change when you have a very fast velocity. And this is high energy. So the velocities are relativistic, close to the speed of light. And so you get this narrowing of the beam. That's quite common, actually, these relativistic jets. What's more difficult to explain or to understand is why it only goes to one side. And I don't have an answer for that for M87. I don't know if there is one. I think it's rare to have something that's only emitting a jet to one direction.
Yeah, that's a better question than the one I asked, actually. Now that I think of it.
One leads up to the other.
Yeah. Okay, thank you.
Any more questions? Okay, if not, I'll stop the recording. Yehu will be here in 20 minutes.